Welcome to our presentation on the paper Minimax Learning of Interpretable Factored Stochastic Policies from Conjoint Data with Uncertainty Quantification. Let's begin. Conjoint experiments are useful because they randomize complex profiles and reveal multidimensional preferences in contexts ranging from policy analysis to marketing and beyond. But they are often analyzed in a marginal fashion, the effect of one feature after averaging over all the rest. This paper asks a decision-relevant question about how all the features combine to determine choices. What full profile strategy, full over all features, should be learned from these randomized data, especially strategies that will be robust to adversarial environments? At least three things make this hard. First, actions are exponential. Every candidate profile is a combination of factor levels. Second, interactions. Good marginal parts may form bad bundles if those parts, when combined together, counteract each other. Third, once we optimize a policy, inference has to follow through the whole optimization process. More concretely, a forced choice conjoint already gives us logged actions. Respondents compare two randomly generated profiles, and the outcome is whether A beats B. Randomization gives us clean counterfactual information, but the profile space grows quickly, so many bundles are unseen or sparsely observed. Now, marginal effects can miss exactly the decision structure that matters most. Outsiders may look good on average, and a moderate may look good on average, but outsider moderates may perform worse when together. AMCE numbers averages that interaction into one marginal number. Instead, here, the target is not an isolated feature effect, it is performance across the full profile, including all interactions. So to be more concrete, the target here is therefore a factored stochastic policy. For each attribute, this policy will assign probabilities to its levels, and the probability of the full profile is the product across attributes. This mean field restriction replaces an enormous joint distribution with attribute level marginals. It is interpretable. We can see which issues, traits, position the learned strategy emphasizes. Now, we first examine the average case. Here, one side will optimize against a fixed reference opponent, usually the experimental assignment distribution. We fit here an outcome model for the counterfactual rewards, then optimize the expected reward minus a trust penalty toward encouraging the policies towards the logging policy. The paper gives a closed form solution under a two-way linear model. We then develop a gradient-based optimization approach for GLMs or neural reward models. After optimization, uncertainty has to pass through the map from the fitted reward model to the learned policy. One option here is to unroll every gradient step and differentiate the whole trace. A computationally cheaper option at the converged interior solution is implicit differentiation. Combined with the outcome model covariance, the delta method will yield standard errors for both the policy probabilities as well as the value Q. We also develop a Minimax extension where the strategic setting is emphasized. Here, the difference will be that the opponent is not going to be passive. The opponent instead will themselves have a distribution that they'll be optimizing. The payoff here will be an institution-aware win probability. The Minimax objective will capture the simultaneous strategic adjustment. In the election application that we'll talk about later, institutions map strategies through primaries into nominee distributions, and then nominees will face each other in the general election. In simulations, we check whether the procedures here behave like statistical estimators. As sample size grows, we find that our MSE falls, coverage improves across the average case and the adversarial case. Great. In the US presidential conjoint application, we find that the average case optimization against a uniform opponent implies a vote shares outside of the historical two-way vote shares. However, the adversarial institution-aware restricted equilibrium falls inside that range and is much closer to the 2016 result. Because the output is a distribution over profiles, the paper also scores observed candidates under the learned strategies and summarize the candidate level strategic divergence. In terms of takeaways, the focus here is really on learning policies and conjoints, not just effects. Randomized conjoint data can support policy estimates under combinatorial profiles. A factor stochastic policy class will keep this interpretable and keep variance controlled, and Minimax extensions bring in a strategic component. Thank you very much.